You type a prompt, and seconds later, a finished essay or a complex block of code materializes on your screen. It feels incredibly human, but that output isn't human thought. It is the result of a specific algorithm known as a generative pre-trained transformer. To appreciate what that algorithm does, we have to look back. Before 2017, neural networks read data sequentially, one word at a time. Because of this linear approach, by the time the system reached the end of a long paragraph, it had often forgotten how it started. The transformer architecture fixed this memory loss. But bringing this technology into the strict, data-sensitive world of enterprise business requires looking past the performance and understanding the raw machinery underneath. The major mechanical breakthrough of the transformer is that it doesn't read left to right. It takes in and processes an entire sequence of data simultaneously. It achieves this using the attention mechanism. Instead of looking at words in isolation, the model mathematically weighs relationships between every input simultaneously. This gives deep context, recognizing bank as a financial institution or a riverside, based entirely on surrounding data points. Because the architecture handles this data in parallel, researchers could suddenly train these models incredibly fast, feeding them trillions of words from across the internet. Because the model absorbs trillions of linguistic patterns at once, it develops the capacity to translate languages instantly and the breadth to distill 1,000-page reports into a few sentences. However, that same open-ended nature creates severe friction when you try to apply it to strict corporate logic. The first major flaw is accuracy. Transformers are probabilistic guessing machines. They predict the most likely word. If they lack the factual answer, they will confidently guess, generating false information known as a hallucination. The second flaw is hardware bloat. To maintain that broad, generalist knowledge, these models rely on hundreds of billions of parameters, the numerical weights that dictate how the network behaves. This chart compares the exponential cost of running 100 billion parameter models against standard software applications. Hosting these giant engines requires massive clusters of specialized processors, driving operating expenses to levels that dwarf typical software budgets. Finally, we encounter the trust gap. To utilize these massive models, companies typically have to send their proprietary data out to a public API endpoint. If that data contains protected healthcare records or European user information, routing it outside the company firewall instantly violates regulations like HIPAA and GDPR. A general-purpose transformer is simply too unpredictable, too computationally expensive, and far too exposed for a secure enterprise deployment. This friction is exactly why Treecapital AI engineered Anven, a specialized architecture designed to operate as a sovereign intelligence layer. Looking at this technical blueprint of the Anven stack, you can see how it solves the privacy flaw. The entire system operates completely offline, locked safely within your own private cloud and firewall. To eliminate the hardware bloat, Treecapital replaced the trillion-parameter behemoths with highly efficient, lightweight models utilizing just 3 billion parameters. They achieve high performance on smaller hardware through techniques like quantization and the structure shown here, a low-rank adaptation or LoRa adapter. This module allows you to inject your specific industry logic directly into the model's weights without needing supercomputers to run it. Finally, Anven tackles the hallucination problem through a framework called Retrieval Augmented Generation, or RAG. RAG acts like a strict librarian. Before the model generates a single word, the system forces it to search a private vector database filled with your verified internal documents. If the answer isn't in your proprietary data, the AI refuses to guess. Transformers provided the mathematical blueprint for today's language models, but sovereign architectures like Anven provide the chassis and the vault required to actually deploy those models in the real world.